it also has the property that for every element in the codomain, there's only one element in the domain which is pointing to it. And a function, this is just what we just sometimes call one-to-one. These are good math things to know if you don't already know. And then there are these things called surjections. What are surjections? They are, this is more obscure because Americans don't want to talk about codomains for some kind of reason. Surjections are functions in which every object in the codomain gets used. And so an example of a surjection might be something like this, in which cha-cha, cha-cha, like this. So here, for every single thing in the codomain, there's something in the domain which is pointing to it. And then a bijection, this is sometimes called on-to. And then a bijection is something which is both an injection and a surjection. And in fact, if you have sets which are of finite size, then if it's a bijection, it has to be, they have to be the same size. Okay, so I gave as an exercise, imagine that we have some function from A to B, and A has 5 elements, and B has 3 elements. And the question is, how many injections, surjections, and bijections are there? Okay, so we can sort of make a picture of this. Here's A, here's B, and here are the 5 elements in the domain. Let's just call them 1, 2, 3, 4, 5. And there are 3 elements in the codomain. Let's call them x, y, and z. Okay, and we're going to make functions from A to B. All right, well, the first question, how many injections are there, is kind of a trick question. There just can't be any. Because from 1 has to go somewhere to x, y, or z, 2 has to go somewhere to x, y, or z, that's just the definition of a function. And so since there are 5 things in the domain, you know, by the pigeonhole principle, I suppose, if there are 5 pigeons flying to 3 holes, then there must be at least 1 object in the codomain for which multiple objects in the domain point to it. Okay, so there are no injections, and since a bijection has to be an injection and a surjection, there are no bijections either. But now, the much harder question, I mean, so hard that, like, you know, it's very hard. How many surjections are there? Okay, and the answer is, this has something to do with Stirling numbers of the second kind. In fact, it has to do with this new construct that we just learned. Because after all, what's going on here, what we're really asking is, for it to be a surjection, then we're looking for all the functions in which at least in which something points to x, something points to y, and something points to z. And so we have 5 elements in the domain, and what we essentially need to do is to assign these 5 elements to either x, y, or z, such that none of them are empty. X, y, the elements pointing to x, the elements pointing to y, and the elements pointing to z, none of those 3 sets are empty. And of course it matters which element goes to which element, so these are obviously ordered. And therefore the answer to this whole problem is T53. And what is T53? Well, we know that T53 is 3 factorial times S53, but that doesn't help me because I don't know what S53 is. And so the better thing to do is to compute T53 according to the formula that we just developed. And the answer is, and here I'll do it sort of with some thinking involved. Well, first of all, I just decide for every single element in my domain, where is it going to go? For object 1, there are 3 choices. It could go to x, y, or z. And so I have 3 choices. So that's 3. But for object 2, it can go to x, y, or z. Object 3 can go to x, y, or z. And so for each of these 5 elements in the domain, there are 3 choices. So this is going to be 3 to the 5th. But of course, that just counts all functions at all. In fact, that's the answer to how many functions there are. That is, every element in the domain can go anywhere. But now, for some of those functions, they won't be surjections because maybe nothing will point to z. And so what I now need to do is subtract out possible functions which are not surjections. And here is where we say, okay, suppose that nothing points to x. If nothing points to x, taking x arbitrarily, if nothing points to x, how many functions are there for which nothing points to x? Well, if nothing can point to x, then everything has to go to either y or z. And so for each of the 5 elements in the domain, they either go to y or z. So there are 2 choices. So that's going to be 2 times 2, 5 times. So this is 2 to the 5th number of ways to have a function in which nothing points to x. But that applies also to y and z. And so we multiply by 3. And then we see that we have overcounted, because we've counted all the ways in which nothing points to x, and then we added to that all the ways in which nothing points to y, and we added to that all the ways in which nothing points to z. And so we've double counted cases in which nothing points to x and y. And so now I subtract out, doing a kind of inclusion-exclusion now. What if nothing points to x or y? Well, if nothing points to x or y, then everything has to point to z. And so there's sort of 1 has to go to z, 2 has to go to z, 3 has to go to z, etc. So there's sort of one choice and times 1, if you want to do that. And now what goes here? Well, now we have that was the case in which nothing points to x or y, but we also need to consider where nothing points to x or z and nothing points to y or z. In other words, there are 3 combinations, or if you prefer, 3 choose 2 ways to pick which 2 elements in my codomain are not being used. And this was really like 3 choose 1. Okay, so this is just an example of the exact same logic from the previous problem. If you now do this all out, you get 243 minus, this is 32 times 3, so that's 96, and now plus 3. So that's 243, and the answer is 150. So there are precisely 150 surjections from a set of size 5 to a set of size 3. This is a kind of basic counting problem that you can solve with Stirling numbers of the second kind. Okay, woo!